Hello everyone. We want to welcome you to the EMMC webinar of 23rd of August with Dr. Malgorzata Celuch, who will tell us why to set up a modeling SME when you are a student and tell us about the economic impact of QuickWave. Malgorzata, over to you.
Okay, thank you, Alex, for your introduction, and good morning, everyone. A special thanks to all of you who joined despite holidays, and special thanks to those who wait through all the technical difficulties. Let me first introduce myself. I am President and Senior Scientist of a company, QWED. It's a company of a limited liability type. The actual title of my talk, The Economic Impact of QuickWave Software, was adjusted to the requirements of the Torino session of the EMMC workshop in July. And I gave the main title, Why Set Up a Modeling SME When You Are a Student, essentially to arouse some curiosity, which I guess I got by means of invitation to this webinar. It is true that I was a co-founder of QWED when I was still a PhD student. The company started its operations in 1997, but it was set up earlier, and the decision to go commercial with our modeling was even earlier, and I will try to talk about all those aspects. Since I'm afraid to forget later all the acknowledgements, I shall start with the acknowledgements. The first acknowledgement is to the Horizon 2020 MAMA project, in which QWED participates, and this project is important to us because it's given a new momentum to our research on materials modeling and material measurement. I will be showing you many pictures taken from the electromagnetic simulations. All those pictures will be from QuickWave software. And I also want to acknowledge that all ideas for material measurement setups, which will be presented in this presentation, come from our collaborator and expert, Professor Jerzy Krupka. Also, all concepts of microwave heating scenarios, multi-physics kind of scenarios, come from our colleague and friend, Per Riesman. As an outline of my talk, I realize the EMMC is concerned with different approaches to materials. I will try to explain very briefly what the electromagnetic modeling is, where it starts, and I will also try to explain how the idea of commercialization of our electromagnetic modeling tools came up. Then, as a focus of my talk, I will talk about electromagnetic modeling as a business. And, of course, I am restricted by various confidentiality restrictions, but I will give you some snapshots of the impact that the modeling had on QWED itself and also on our customers and partners. I have realized that an important aspect of the EMMC interests are different workflows of the modeling. We called them previously regimes, but let me adapt to this notion of workflows, and I will show you some specific workflows of coupled models for microwave heating, or a very unique workflow in our software, a freeze-up state. And also I will indicate how different workflows help in kind of technology transfers between different domains. I will show you how we verify and how we validate QuickWave simulations. I will just briefly mention how we follow the different available hardware and software, and I will show you some user stories. Essentially, my interest in giving this presentation, besides presenting you the various aspects of being commercial, is to seek collaborations with any of the participants who have an interest in different aspects of physics, of material science, and who would like to consider collaborations with QWED on linked or coupled modeling. So let me start with the definition of electromagnetic modeling. Electromagnetic modeling is essentially solving the Maxwell equations, which I'm showing here. Just a reminder, probably from high school. These equations are remarkably simple, especially if we take them in the differential form. So for material scientists, it may seem that all that we are doing in electromagnetics is very simple. For us, all knowledge about materials resides in those parameters, permittivity, permeability, and conductivity of a material, which in classical applications of the modeling, by classical applications of electromagnetic modeling, I mean telecommunications, radars, this is where it started. So in those applications, materials are just represented by constants, which bind the different pairs of fields components. Of course, when we switch to multiphysics modeling, to material science, I will show you more complicated ways of our approaching to materials. There are two perspectives of electromagnetic modeling. In the classical way, in the classical branch which I mentioned, it's essentially electromagnetic wave propagation in space or in transmission lines. When we go to field interaction with materials, we encounter new problems, but also new challenges, new interests in the modeling of, for example, microwave ovens, but also biomedical applications, microwave chemistry, microwave pharmacy, and QWED has also been involved in such curious applications as rock comminution assisted with the microwaves. As an example, the first example of cases where the material cannot be represented by just a constant are so-called dispersive materials. This dialog shows you, this is the dialog from our QuickWave software, which shows the type of materials which we can consider. Dispersive materials are such that one or more of their characteristics, like permittivity in this case, is a function of frequency. And you can see here how water parameters change as a function of frequency. This is what we have to implement in modeling. Or we can also see such curious applications, such curious materials which in some frequency subranges have negative values of permittivity, negative values of permeability, which means that the E and D fields are actually oriented in the opposite directions. So that's just an extension of the basic electromagnetics. Electromagnetic modeling is simple, but still simple compared to many other topics in material science, but still the possibility to solve those differential equations with arbitrary boundary conditions was limited at the time when computers were limited. So when we look back into 1980s, this is when I was a master's student, the state of art was such that the actual design of microwave devices was accomplished either through heuristic equations, we would call them data-based models, models based on early experience, with lumped circuit approximations where we assume that fields do not vary in space, they don't vary in time. One-dimensional approximations, well-known telegraphist equations or notions such as Smith chart. And in the 80s and 90s, the academic research on solving Maxwell equations for two-dimensional wave propagation, three-dimensional propagation was actually starting. That was the time when we were getting many publications on different methods of approximating fields in space and in time. Without going into too many details, I may mention that the finite element approach, I noted it here in blue, I get an impression that this is the major approach for solving material science equations, while in electromagnetics it is just one of very many approaches which we find not only in literature but also in the actually available software. Additionally, we have finite differences, finite volume, transmission line matrix approach, spatial network, many other ones. And I will just mention that was my research from my PhD times. We confirmed that for our purposes for solving the Maxwell's equations, the finite difference approach and conducted in the time domain is the most effective in terms of computer resources to accuracy. So here I'm just showing where we are located with the QuickWave tools I will be talking about. And in the 90s, which is where the story of QuickWave will start, the questions that microwave engineers were asking was, will electromagnetic software really help me? Can it give me any extra advantages on top of what I already know, the one-dimensional or heuristic approaches? So is it really helpful? Today there is no doubt the software is helpful, so for us that's a good news because there is a market for the software. There are people who want to use it, but there are still notions. Can I trust it fully? Can I completely skip the hardware prototyping? And also the bad news is that quite a lot of electromagnetic software has come up to the market. This is a list of representative publications. I'm not going to talk about it. It's mainly for the sake of recording. It shows you the beginning of electromagnetic modeling at the Warsaw University of Technology. It was originated by QWED co-founder, Professor Gwarek, with his pioneering papers in IEEE Transactions of Microwave Theory and Techniques. The value of those papers has been acknowledged by IEEE by awarding the Pioneer Award to Professor Gwarek. And I went in at this stage and I started actually investigating the concept of finite difference time domain approach, and my interests were mathematical. So that should be clear. I'm an engineer by education, but not by passion. And I was mainly looking into the mathematics of the modeling, and I was asking questions, well, should we really do finite differences time domain, or maybe the transmission line matrix method, which was extremely popular in terms of number of publications and also money invested in research in the 90s. I was also looking at finite element methods, and I published my first conference paper in '91. It was quite unique being in Poland just at the time of political changes to have a student's paper accepted for the international conference, to have it presented at the conferences. So I was happy, and I was feeling to be very much in the forefront of research. But what happened next was that I had enormous problems of pushing my papers through reviews to journals. One of the stories was that the paper based on this conference paper from '91 was first accepted for some journals, subject to minor changes. Then it was rejected, then it was accepted again, then it was lost. It was quite an unbelievable story. And we only had suspicions that maybe the problem was that our reviewers were passionate about the TLM method, and I was essentially saying that financing of the TLM maybe goes too fast. I was not using this word, but I was showing that FDTD was more efficient, and it was not a good message. And maybe I was not clear enough in expressing my views. Anyway, after a few years of publishing many conference papers and publishing some so-called innocent papers, not changing the people's views, Professor Gwarek and myself, we found that pushing our main ideas into a big journal is extremely difficult. It may actually be easier to prove our point on the open market. And that's how we decided to try and go for a commercial version. So I put it nicely that this business of QuickWave was born out of obstacles. I would even say it was born out of a kind of scientific, quasi-scientific rejection. Anyway, we decided that the market was a more fair forum for proving the point. And at about that time, 92, 93, we decided to go commercial. I will show you in a minute how. And when the software came into the market, also all the delayed papers were published in the late 90s, but the software was already operational and proving itself. So when we were setting up this business, when we decided to go commercial, did we have any idea of a business? Let me just remind you that the political system in Poland changed in '89, so we were in a country which was changing, the economy was changing. Many educated economists were telling us that all their education became suddenly lossless. I was not completely ignorant about business. My father was working for Polish foreign trade. I knew something of it from my childhood, but I simply did not ask any questions about any penalty that I may pay for having a business failure. It was very optimistic, very maybe ignorant, but we just did not think there could be any trouble, any penalty associated to our change of approach to the modeling and our change of lifestyle. I presented here some snapshots from a BBC lecture exercise about the advantages and disadvantages of going commercial. So looking back, as I said, I was not asking those questions in the 90s, but looking back, I would say that I never thought about profit in terms of additional money. I did not think the modeling would bring us money. I did not quite think of satisfaction of being independent, because for me being a scientist was enough satisfaction. I didn't think about being able to make to contribute to charity. I was already involved to other ways of other charity organizations. But my only expected reward from having the business was the satisfaction to prove my research concept. And I did not expect, as I said, any penalties, any particular difficulties. So how did we start with marketing, if we can call it marketing, of QuickWave once the software was put into some usable forms? I highlighted some points some things which happened, and some of our approximations, assumptions which were proven true. First of all, people trusted us. So when we launched QuickWave onto the market, people in, for example, radio astronomy in the United States, they knew us by names, and they wanted to try what we've come up to. So the trust of our previous collaborators, of sometimes competitors, helped us get onto the market. We also trusted very much our choices. We had no doubt, based on the research, that the approach which we had chosen, the finite-difference time domain approach, was the correct one. And we were not afraid to approach very difficult examples which were proving too difficult for various other software. And this is a testimony from our users about how things happened. And we were also not afraid to take up challenges and, for example, to develop new functionalities from scratch. Today I find it unbelievable from the perspective of QWED, and I suppose it's even more unbelievable from a perspective of any bigger software vendor, is that we could take up a new concept from a customer. This is an example of developing a ferrite model, which was needed for crisp plates for microwave ovens. These are plates which allow you to make pizza in a microwave oven. And from the idea to the time when we provided a new version to our industrial customer was just 2 weeks. So we were not afraid. We were jumping into any opportunities, into any challenges. And what we found at one stage was that our clients were becoming our biggest marketing force. Simply one client was recommending us to another. We also trusted what our expert users told us about the market. We had testimonies of our experts telling us that FDTD was outperforming the finite element method approach. So that all looked great, but we of course also made mistakes, or we simply did not know things. So first of all, we underestimated that the popular market, not the expert market, wants things to be easy. Engineers in industry often don't care too much about the accuracy of the software. They want it to be very easy, they want to set up problem easily, and they want to get some answer, not necessarily the best answer. And our software was very complicated. We thought the software should do everything. We thought we should take into account all possible options. And as a result, it was quite difficult to navigate through. And what we also underestimated was the responsibility. It was especially true in my case. I did not think how difficult this responsibility may be to bear towards the users who always expected new results and new functionalities, and also employees. When we started employing people, we found it was very different from being in the academic environment where your students simply get their scholarships or get their salaries. In a company, you are responsible for earning money, for providing it to your team. The start of QuickWave was based on our research, and it was funded from our own pockets. We got small funding of a Copernicus project. It was the first scheme that Poland, the first European scheme that Poland was allowed to participate in. Unfortunately, that Copernicus project was closed very quickly because of bankruptcy of our German partners, so no fault of ours. And in '96, we were left with the software which we were developing with a view to commercialization, but we were thinking of commercializing it jointly with the German partner. In '96, we had to decide what to do about the software, which was in its infancy, and we had no experience with writing manuals, we had no experience with marketing. But we decided to go on. What's important, we did not get any funding for software development anymore. And for many years, we were not getting any projects, any grants, any contributions in kind, and we were not taking any bank loans, which allowed us to be independent, but set up some limits for what we could do. So with the decision to continue in '96, just the 4 people, 4 main authors of the software, keeping our academic jobs, which meant we were full-time academics and devoting our spare time, so-called spare time, to the software development, we brought it to a level when in '97 we got first sales to Sub-Erickson Space, to National Radio Astronomy Observatory in the US, to Caltech, a leading university, and also to JPF. We formalized our company in '98 to the Ltd type. It was previously partnership. We had an idea that we should join forces with a bigger company taking care of worldwide distribution, and we had an agreement with Vector Fields, a UK company, vendors of Opera software. That collaboration developed very nicely, but Vector Fields were later acquired by Cobham Corporation, and collaboration became difficult, so the agreement terminated. And we continued ever since just on our own, also with marketing. Our current workforce is 13 people, it's 4 main co-authors and our permanent staff. The team is led by 2 state professors and 2 PhDs. All our employees have at least a master. And you can see we are very well balanced in terms of gender. that varies period to period, but essentially 50% of the company are female engineers. And we are hiring, just a note in case anybody wants to experience working in SME in Poland. I can just indicate here that our business profile has been changing. So when we started sales in 97, 98, we were a new product onto the market. There was a period when we had a full license sale every month. So I would say the money was coming in. But essentially, at least I used it for, well, putting my own life back on track, because previously we just economized on everything to have time for the software. So the income was coming from licenses. In early 2000, we started distributing hardware for material measurement, and also we started getting European projects in FP6 and later FP7. Today this profile is changed, and you can see in the order of profit which branches give us more. So this is how QWED looks 22 years since its establishment. First of all, let me point out that our three branches of activity. The first is electromagnetic simulation with the FDTD tools in three-dimensional version, in axisymmetrical version. It's based on our application. It has been rewarded by, for example, the European Information Technology Prize or the Polish Prime Minister Award. The second branch is test fixtures for precise material measurements of electromagnetic properties at microwave frequencies. They are portable, nice, and easy to use devices, again awarded with Eureka and also Prime Minister of Poland awards. And we are also involved in consultancy and design services. On the right-hand side, I'm showing you the projects with public funding which we completed. All projects were application-oriented. They were not concerned with software development. About applications, the original ones were antennas and feed systems, very much for cosmic research. The small insert shows a waveguide feed designed at the National Radio Astronomy Observatory. And what I want to emphasize is that the National Radio Observatory, Radio Astronomy Observatory, publishes its results. For example, the results connected to the development of Large ALMA radio telescope in Atacama Desert. They are all available at NRAO web pages. So this is what I meant by saying that our customers were becoming our marketing force. What was quite unique for QuickWave is that we can treat very large geometries, and we have a special version for actually symmetrical structures. So we can treat objects which are now even 3,000 wavelengths in size. Some successful user cases related to the use of the software. This slide shows snapshots from the websites of our customers who acknowledge using QuickWave. These are also logos of several universities selected from the many universities which use our software, so academic use is important to us. What's nice to us is sometimes to see that the knowledge of QuickWave and its operation becomes a prerequisite or a desirable feature of candidates to be employed by prestigious institutions such as the National Radio Astronomy Observatory. And again, maybe I will not read all text but it will be available in the recording. This is a selection of testimonies of our software users, also indicating what kind of advantages they got from the use of the software. Let me begin with the professional software review by IEEE Microwave Magazine, which in 1997 said that QuickWave software promises to be a gem. So when we look at testimonials after 1 or 2 decades of use of the software, there are testimonials related to a decade use of the axisymmetrical version of the software, which keeps running 24/7 for design of antennas in Australia. There is a testimony from Caltech and JPL from Dr. Peter Siegel, who actually considers QuickWave the most intuitive, quick and easy to use simulator. As I said, many engineers have a different definition of the ease of use, but at least in research, our approach is appreciated. What essentially all our users agree is that our technical service is unmatched. So our technical support always sometimes goes more into consultancy than pure technical support. We find it difficult to define the limits. Now, I'm essentially not allowed to use names of our big industrial users, but since one of our users refers to the companies for whom he worked with our software, I guess it can stay on the slide without me saying who it was, but it is true that since the 90s, late 90s, QuickWave became also used in the design of microwave ovens, which is where material science will come into play, as I will show on the following slides. So when microwave oven producers started using QuickWave, they quickly said, well, hello, this is excellent electromagnetics, but materials are not so simple. Materials are not described by scalars. As a result, we came up with a module which we called basic heating module. We thought it was the very first functionality needed for the modeling. What this module does, it automatically changes the material parameters during the heating. So when we model the heating, as we model the elapsing time, the material temperature increases, its parameters change, and this is automatically taken into account by the software. This name basic heating module stays as an acronym BHM, even though today it's not anymore basic. So the first, I'm not giving the name of the user here, was a very funny comment we received from the user who said that when he was modeling a sausage, he had to take into account that every piece of that sausage will be heated differently, so it will come up to different temperature and hence different materials parameters. With our model, he no longer needed to define 100 different materials, and he was happy. Those developments were used in microwave physics. They were especially helpful in the progress of defrosting. Again, I will show examples on the following slides. And I guess the best testimony is from Per Risman, now with Malgorzata University in Sweden, who says that the use of our not anymore basic heating module did a lot of experimental work, obsolete, and saved both time and money. And I'm making a note here about the fact that QuickWave approach is to offer interfaces to software solving for different physics, and we are open to collaborate on coupling electromagnetics to any other physics. A very nice microwave oven from Whirlpool, and we are allowed to use this model for our publicity. This model is also described in the actual behavior of this very real, very nice microwave oven is presented in the book, in which I co-authored one chapter in its first edition in 2009, and in a few months the second edition will be issued by Elsevier. any of you interested, I would encourage you to look into this book for the fascinating world of microwave heating. We used the multi-physics modeling, for example, to model drying of food waste on ships, or for a microwave applicator for repair of bituminous surfaces. And this is actually an example described in the application. This is an example how, with the use of the software we designed ourselves at QWED, we designed the full apparatus which was later tested on the road. How our approach to coupling and to multi-physics modeling works. As I said, when we model the electromagnetic process, we find the dissipated power pattern. We know that as a result of power dissipation over some time, the enthalpy increases. Enthalpy is transferred into temperature. This can be used through constant material parameters or through user-defined text files, which can come from measurements or different types of approximation. We are able to consider load movement, load rotation. Recently, we added fluid flow modeling. We take into account heat transfer, and when we have new temperature of materials, we update material parameters. When we update material parameters, of course, the previous electromagnetic solution is no longer correct, so we come back to the electromagnetic solution to find a new steady state. So this is the first coupled workflow which I'm showing here, and which has interfaces wherever you see arrows. These are actually interfaces where any additional models can be connected. To maybe as a kind of lunchtime remark, let me note that typical foods have parameters strongly varying with temperature. For example, beef, if you take a frozen beef burger for lunch, it has permittivity 4, and when it is heated to room temperature, its permittivity is above 40. As for conductivity, initially it does not conduct microwaves, and later it's very strongly conductive. So if we try to simulate the heating of our frozen beef burger, we would get this kind of pattern with very small heating and in the center. When we consider a beef burger which is heated from room temperature, the heating pattern is different. With our coupled module, we see the effect of so-called thermal runaway. The heated parts heat faster, and we get this undesirable hot pot. This is, of course, the result of using a microwave oven which is not so good, which has to be redesigned. During QuickWave modeling, after every portion of the heating, material parameters change. So now the colored pictures are not a distribution of temperature, it's not a distribution of electromagnetic field, but this is actually a distribution of material parameters. So you see the material parameters become different at every point. How we verify and validate our modeling verification. I'm assuming here EMMC terminology, so verification will be against previously verified models or analytical equations. We show here verification with respect to other software available on the market. You can see that all the software, electromagnetic software, which is on the market, all the good software, agrees that the simulation of return loss from a microwave oven loaded with a potato, but the differences in time taken by each of the software packages for reaching the solutions are by at least an order of magnitude. And QuickWave tends to be the fastest one. We also validate our result by comparison to measurements. And this has certainly been done by the designers of the oven because before they launched the oven onto the market. I want to make here a remark about a very unique workflow in our software, which is a freeze-off state. Sometimes electromagnetic simulations may take days. And sometimes you want to break the simulation because, for example, you know there will be a power cut. or because you want to freeze the simulation at some stage and later show the steady state development to your students or your customers or your superiors. So this feature is implemented in QuickWave, and as far as I know, we are the only software which offers this functionality. We have workflows for collecting data in a grid search. So we perform grid search, changing some parameters of our design on a grid of values, and we dump either the results for every solution or we dump pictures obtained during the solution. We have so-called Nearfield Workflows, which simply means we can observe electromagnetic field patterns. That's important in microwave design. For example, we show here two examples where you can see spillover. Spillover means that the field, instead of going in the desired direction of radiation, they are spilled around the edge of the reflector. And with QuickWave, we are able to not only to see the spillover, which is also detected in measurements, but we are able to explain its physical causes and to propose remedies. And the causes can be very different. This is one cause when the shape of the reflector was the reason, and the change of the shape of reflector could help. But there is another example where actually the cause of spillover in this distance zone from the actual feeder was due to a resonator formed on the actual feed. With the use, a second kind of internal application success story. I was showing you application success stories in the form of microwave ovens from our design by our customers, but we have our internal success story, which means that electromagnetic modeling has been used to design a simple apparatus for material measurement. So what you see in this picture is a full setup consisting of a dielectric resonator, a Q-meter, which is a portable device which replaces big and costly vector network analyzers for this application. And the whole setup, controlled by a laptop, allows you to measure material parameters. Those units are easy to use, and the current sales of QuickWave are at the level of 10 units per month. So that's how we put our modeling into the actual device. The slide shows the family of devices which we offer. Keysight Technologies recommend our resonators as an extension to their vector network analyzers. So this is again the case when a big company does the marketing for us because of thanks to their channels. About linked workflows, what we are able to do is to model two scenarios and later in a linked manner to consider the sum of differences of the solution. This is an example. This is the model of our dielectric resonator, which we model without a sample and later with a sample. The model is constructed in the industrial environment in Autodesk Inventor. And by comparing the fields in two cases, we are able to verify the assumption of dielectric resonator measurement, which is that the electric field in the two cases without sample and with sample should not differ. And we compare that the difference of those two linked models is at the level of 0.2%. This approach of calculating two scenarios and considering the difference is informative in many cases. For example, to give something human to this presentation, Per Wiesman at the Malgorzata University uses this regime for detections of tumors and hemorrhages. So in reality, the difference between fields was between the fields radiated into a healthy and not healthy head would be taken from measurements. Doing this in simulations helps in constructing antennas for performing medical imaging. We can also detect by taking difference between two scenarios. We can, for example, detect the reason of the exploding egg effect. I don't know if any of you have ever tried to heat an egg in a microwave oven. If not, don't do it in your own oven. If the egg explodes, especially if the oven has a grill, there may be a problem. But it is known that the wave impinging on electromagnetic wave of frequency of a microwave oven impinging on an object of the size of an egg focuses in the center, but now the difference of fields without an egg and with an egg shows us that the reason is actually the external resonance around the object. This is an example where when we take material parameters from external databases. So this is the model of an Austin man, which pulled the research of the Malgorzata University. We incorporated into QuickWave for what they use, and we read parameters from an external database, parameters of tissues. We are, of course, doing our best to follow hardware breakthroughs. The two pictures show you how the speed, let's say the height of the bars exemplifies the speed of the solution. It's in linear scale. We see how the speed of the solution, the speed of the simulation changes with the use of different hardware. I'm not going into details here. I will be happy to answer some questions. But I would like actually to give a warning here. Not always following hardware development is cost effective. At the very beginning of using graphic cards, we had an experience of using very customized cards for solving the FDTD equations, and we invested a lot of our engineering time, which to an SME meant also a lot of money. And that was an investment which actually never gave us any return. However, now coding ourselves on graphic cards is the future. This is a profitable approach. It's profitable to our users. And again, the unique feature of QuickWave is, contrary to our competitors, we do not need professional graphic cards. We can also use cheap video cards. A few remarks about how we enter data into QuickWave Simulator. I have already mentioned the Autodesk Inventor software as an industrial interface, so the users who have the software can just use QWED plug-in and launch electromagnetic simulation from exactly the same user interface which they may have previously used for mechanical or thermal design. We also have our own editor, which uses parameterization of objects. And now we have a new business model, which is actually a modeler developed with the use of FreeCAD libraries, which means we can make it available for free. It's license free, so anyone can download the modeler and see how it works and set up geometries. You don't need license, you don't pay anything, you have no limitations on how many people work and how many projects you prepare, and it's only when you have your scenario prepared you need the simulator license to get the electromagnetic solution. So this essentially completes my talk. So I gave you some snapshots of how we understand the electromagnetic modeling, what we do. I made a focus on the different workflows, but what I was also trying to show is that having the workflows I implemented based on the user's request. But having different workflows helps you bridge the gaps between seemingly different technology domains. So this linked approach of taking a difference between two models is used for explaining the exploding eggs, but also in material measurements and also in biomedical applications. I have shown that coupled models are necessary for microwave heating to be able to follow the variations of material parameters during the heating. But here note when you use such models, you need to very well understand both aspects of the physics. Using just electromagnetic solution as the input to, for example, a thermal solution does not give you a full picture, and this is what we are showing in the Elsevier book, which I've previously mentioned. For those of you who may be considering going onto the market, I would like to attract your attention to the two approaches to software development. One is a black box. So you have a solver, and you input geometry, you input some parameters, you get solutions, meaning numbers. You get some solutions. Many people are satisfied with this. This does not give the full physics, but this is what many engineers will like to have. Unfortunately, many engineers are not interested in the full understanding. When you take the other approach, you change your software into a virtual laboratory. You want to have access to all the available data. This is what we have in QuickWave. At any time, at any point, you can inspect any field component. So this is your virtual laboratory. It gives you full physical insight, but it is more difficult to use, and if you go for this more difficult approach, it does not mean that all your users will appreciate it. I've shown you that it is possible to set up a business just based on the research idea. So the company set up in 1997 still exists, and it's doing very well, even though we never got any initial funding, we never got any forms of support. We never took any bank loans, but the price to pay for setting up a business, it's not necessarily financial. It actually involves the change of your lifestyle. You have to think of your company. I find myself never forgetting about things to do, and there are always things to do better, and there are always markets to fight for, and there are always new applications you want to consider, and all this leads you to a vast responsibility towards the people who join forces with you, and also towards your customers. So even if the product is announced a gem, as it was the case in QuickWave in '97, this gem does not shine forever. And to continue the business, you may need to consider different schemes. It's not just licensing, it's a combination of consulting, design, R&D projects. In our case, having our own hardware designed with the software is very helpful to be able to further design the software. And I would also like to attract your attention to QuickWave Modular, which we find is a new business model. We are hoping it will give us new perspectives. The approach where the user does not need to pay anything to get acquainted with the interface, to prepare projects, and to later decide which solver licenses are needed. So to finalize, I thank you, and I'm seeking collaborations to further link and couple our electromagnetic modeling to other branches of material science. Thank you.